Welcome to The Explainer. Let's dive right into something that happens every single day in classrooms. We are taking a really fascinating journey into the minds of elementary students to figure out exactly how they develop geometric thinking. We're going to explore how we can help students go from just identifying shapes by sight, just eyeballing them, to actually gaining deep analytical insight into their mathematical properties. Whether you're an educator or honestly just someone fascinated by how the human brain grasps spatial reasoning, you're going to love this breakdown.
Okay, so to kick things off, let me ask you a question that highlights a totally relatable classroom phenomenon. Why is it that when you show a young kid a square, they correctly call it a square, but if you simply rotate that exact same piece of paper so it's tilted on its point, they suddenly call it a diamond? I mean, diamond isn't even a mathematical term, yet it happens all the time. Well, this little anecdote actually reveals something profound about how children naturally perceive the world. It tells us that for young minds, the overall appearance of an object completely overpowers any of its underlying math properties. To them, it's not a rotated square at all, it's practically a completely new object.
Section 1. The Van Hiele Theory of Geometric Thought. To figure out why the whole diamond thing happens, we need to look at the foundational framework behind spatial reasoning.
So this framework, the Van Hiele Theory of Geometric Thought, was actually put together by two Dutch educators. It's a 5-level developmental hierarchy that describes exactly how people learn spatial ideas. You start at level 0 at the absolute bottom and work your way up. Now the key here is that it's experience-dependent, not age-dependent. But realistically, most of the elementary students we're working with, they are operating right down there at level 0 or level 1.
Here's the fundamental difference between those first two levels, and it's absolutely crucial. At level 0, known as visualization, appearance rules everything. A student might look at a shape and say, oh, it looks like a rocket, or it's curvy. But when a student reaches level 1, which is analysis, it's like a light bulb goes on. Their object of thought shifts from single, isolated shapes to entire classes of shapes. They stop talking about this one particular rectangle and start pointing out the properties all rectangles share. Stuff like parallel lines, right angles, and opposite sides being equal. All those irrelevant features like how big it is or if it's tilted finally fade into the background. So obviously moving a student from level 0 up to level 1 is our primary goal in early geometry. But how do we actually do that? Well, we have to be strategic. First, we challenge them to test their ideas using a whole variety of examples. Ask them, okay, but is that true for other rectangles? Second, we have to provide a ton of opportunities for them to physically build, put together, and take apart shapes based on specific attributes. And third, we push them to apply their new ideas to entire classes of figures, rather than just staring at one individual shape on a desk.
Section 2. Sorting and classifying shapes. Let's transition from the psychology of how they learn straight into the actual classroom activities that make this cognitive leap happen. Just look at the sheer variety of 2D shapes you can use for this. In shape sort activities, you literally just hand a group of students a massive, diverse pile of shapes and ask them to sort them into groups. But here is the secret sauce. The students, not you, not the teacher, must decide the rules for the grouping. If you listen in and hear them sorting by things that are pointy versus shapes with right angles, you can instantly in real time diagnose their current Van Hiele level. It's a total game changer.
Now, to actively push them toward level 1, games are your best friend. In a secret sort, you, as the teacher, create a hidden rule. Let's say shapes with at least one right angle. As the kids try to guess your rule, they are literally forced to look past what the shape overall looks like and zone in on specific properties. When they finally notice it and call it a square corner, you just naturally step in and say, yep, we call that a right angle. Another fantastic game is What's My Shape, where they ask yes or no questions to guess a hidden shape. They learn real quick that asking, does it look like a house, isn't nearly as helpful to winning the game as asking, does it have parallel sides?
All right, Section 3. Composing and decomposing. Next up, we need to talk about putting shapes together and taking them apart.
This isn't just playtime, folks. Composing and decomposing is heavily tied to their future math success in stuff like fractions, area, and volume. To make it tangible, we use some great physical tools. You can use the 7-piece Van Hiele mosaic puzzle, which is built on an isometric grid, and it's absolutely perfect for exploring how smaller shapes compose to make bigger ones. Or you can use a trusty geoboard. Geoboards are incredible for decomposing. You can challenge a kid to build a crazy complex shape with rubber bands, and then ask them to figure out the fewest number of triangles they need to subdivide it.
When they divide a shape into equal parts on a geoboard, they are quite literally building their foundational understanding of fractions with their bare hands. Up next, Section 4, defining polygons and solids. Once students really have a firm grasp on properties through all that sorting and composing, they are finally ready for the formal definitions. When we break down the formal subcategories of polygons, a level 1 thinker is totally capable of defining a square as a parallelogram that happens to have a right angle and all equal sides. But as educators, we have got to remember to present these shapes in all sorts of weird orientations. If a student tells you a triangle is upside down, that simply means they haven't had enough experience seeing triangles in the wild spun around in different ways. A scalene triangle is still a scalene triangle, no matter how much you spin it.
And you know what? The exact same logic applies to 3D shapes, or solids. There is this huge common pitfall where even textbooks will limit the definition of a cylinder to only shapes that have circular bases. But mathematically speaking, a cylinder is simply a solid with two congruent, parallel faces connected by parallel lines. Mind-blowing, right? That means prisms are actually just a special case of a cylinder that happens to have a polygon for a base. Getting them to understand this inclusive definition early on is incredibly helpful, because later down the road it means they realize one single volume formula can apply to any type of cylinder, including a prism.
Section 5, Tools for Geometric Construction. To truly cement all these abstract definitions we just talked about, students need to get their hands dirty.
We have to let them physically construct their own geometric representations. One of the absolute most exciting ways to do this is by building giant, skeletal structures out of nothing but tightly rolled newspaper and masking tape. If you roll the paper super tightly on a diagonal, it makes incredibly strong sticks. This is a high-energy, totally chaotic group activity, but man, they quickly discover real geometric concepts like rigidity. They figure out real fast that they absolutely need triangular components, or else their massive 3D structure is just going to pancake onto the floor.
Now, let's look at how this builds in a digital environment. Dynamic geometry software, think programs like GeoGebra or the Geometer Sketchpad, is revolutionary. If you draw a quadrilateral on a piece of paper, you're stuck observing just one single shape. But in dynamic software, you can grab the points and drag, stretch, and warp that quadrilateral into an endless variety of shapes, and the software updates all the measurements instantly. If a relationship, like the midpoints forming another quadrilateral inside of it, doesn't change even when you turn the shape inside out, students suddenly have actual proof that a property belongs to a whole class of shapes, not just the one drawing they did on their paper.
And that brings us to Section 6, Transformations and Line Symmetry. This is our final topic.
In elementary education, the broader study of transformations, like translations and rotations, is usually saved for middle school. Instead, younger students explore transformations primarily through the lens of line symmetry, and the definition we use is beautifully simple. If a shape folds exactly in half, that fold is a line of reflection. We want to anchor this potentially abstract concept of mirror symmetry in the physical, totally tangible action of folding a piece of paper. The portion of the shape on one side of the fold is literally reflected onto the other side.
To make this concrete, we rely on highly visual, hands-on activities. Students can literally fold paper and cut out shapes to see the symmetry unfold right in their hands. They can stand a physical mirror up straight on a design on their desk to see the completed symmetrical image. You can challenge them to build half of a design with pattern blocks, and then complete the mirror image, or have them draw exact reflections across a drawn line on a dot grid. The whole point is moving them from just recognizing symmetry visually to actually creating it mathematically. To wrap up, I want to leave you with this provocative little mystery definition riddle straight from our source material. Take a look at this. The top group, labeled all of these, have something in common. The middle group, none of these, do not have it. Based on your own geometric thinking, which of the shapes in the bottom group belongs with the top group? Notice what your brain is doing right now. You're frantically hunting for properties, checking angles, looking for symmetry, rather than just deciding based on what the shapes look like. That means you are analyzing. You aren't just visualizing. Keep testing your own geometric thinking and consider how you can apply these hands-on, structured activities to help learners discover the incredible architecture of the shapes all around them.